In this discussion, I want to talk about an above threshold derivation discussion about what a differential pair circuit looks like. Sort of a structure like this. I'm going to kind of assume there's no sigma, no dibble, no channel length modulation, so I can just kind of look at these devices and go, well, what does it look like for an above threshold derivation? Now, you may have seen a derivation of this in subthreshold, and in such a case, it's a fairly straightforward and clear kind of approach. But in the above threshold case, it requires a little bit more thinking through this. And if you take nothing else away, you begin to realize that as soon as you get into above threshold, the conversation gets more complicated than it would be in the subthreshold case. And so this is really important to think about, okay, so how do I approach it, and what kind of questions do I often run into, and what are the issues? One of the things you don't cross at all here is because we say sigma is equal to 0, there's no channel length modulation. I've already eliminated that part of the conversation, which often complicates some of these systems. But we're going to start there. Now, what do I end up seeing here? Well, this lower device is basically acting like a current source. It pretty much sets a bias current of IREF. And then I have two other transistors, this one for V1 and this one for V2, where there's a middle node in between that kind of sets the equilibrium that sets I1 plus I2 equal to IREF. So that's kind of where we start. We're going to assume all the devices are identical, so that way it just kind of keeps all the math simple. And we'll be able to kind of run through things accordingly. And that, of course, accordingly for that, we get the sum is equal there to the IREF. IREF also gives me k cap over 2 times Vref minus Vt0. So this is what you get for above threshold for that device. I1 and I2 give you similar expressions, but you have your term for the source term in it. And remember, in the source term, you've got a kappa. So do not forget the kappa. That will be kind of important for these structures. Now you can do things without it. You can kind of assume kappa is 1. The math turns out to end up being very, very similar and equally kind of a struggle at times. But we're going to kind of work through this. So what you can then do is say, well, okay, how do I think about I1 and I2 as a function of IREF? Because this is kind of what we did in the subthreshold case. Because what we're trying to do eventually is get them in some sense of that so I can actually deal with the V node. So this is where we begin. And you can kind of rewrite it in this very interesting, strange case, which basically gets rid of the k kappa over 2. It's one way to approach it. By the way, this is one way to go. There's many different ways to kind of work through the math and see different pieces. The other thing I want to do is I want to get my definitions of the inputs in sort of what is sort of common between the inputs and what is differential between the inputs. And so in this case, what I'm going to find is that the difference is going to be sort of half of the difference between V1 and V2, and the common is going to be the average of those two. Very typical definitions, but that's kind of where we're going to begin with it. And so doing it means I can make V1 and V2 equal to these sum and difference of the differences, and plug that into the expressions, and you go, okay, that just got a little more complicated, but it's fine. Remember, Vref is fixed, Vt0 is a known quantity. Nothing too shocking there. Kappa is a known quantity. So just kind of keeping in mind what is important. Well, at this point, I can then say, well, what is the sum of these two? And the sum of these two equals to IREF, which is then going to be equal to IREF plus a bunch of stuff, plus all of those elements. And you think, okay, now I can make sense of it. Another thing is if I have the sum of squares where almost everything in the squares are the same except that the sum and difference is there, what it means is I get the things on the edges, right? I get the one aspect squared are all in common on one element, plus the other thing squared, because then the things that are different are going to basically subtract out. I can take that expression and eventually solve for what is the common part, the Vc minus Vt0 minus V over kappa, and that gives me this term here. And you can kind of see the Vref minus Vt0 squared. You can also see the minus Vd squared. And that's what starts to make, so that kind of gives us a sense. And what it says is that, for a given reference voltage, that's going to pretty much set, for a given VC, And V, that's going to be determined by what the reference voltage is. And there's some effect and pull because of the differential voltage. Because again, if V1 or V2 is much larger than the other, that's really the thing that's setting V. And so we kind of want to make sure that's all being taken account for. That being said, I can then say what is the thing I really care about, which is the difference, I1 minus I2. And I get a similar thing, but now I use the geometry in a different way. And if I subtract two things that are similar, but there's some difference in what's in the square, it's what's different in the square that remains. And so that's why I get this term here for 4V ref times these terms, and there's a VD that comes at the end of it, because that's one of the difference things in it, and this is the other part of that. And so that works great, but I also know what this term is because I solve for it up here. So then I take that and I substitute in and I go, oh look, now I have an expression of I1 minus I2 as a function of just the differential voltage. And this is what I was eventually wanting to get to, right? Because I should imagine that it should primarily be a function of the differential voltage and not anything in common. Now again, remember I said sigma 0. Sigma wasn't in 0, we're going to get some extra terms. But this gives you the rough sense of that. This gives you the analytic sense of that. And so then you can kind of rewrite everything in this nice form, and everything tends to go fairly smoothly here. And you go, well, that's great. And you can kind of see that there is kind of a linear term, but then something that kind of saturates you off. This term is going to be correct up until, the slope is positive. It eventually will flatten out. So there's a limited range over this expression being accurate because of the assumptions that were made. But here's the thing, if you actually plot those curves out, then you say, well, what happens for a certain V ref minus VT0? Say that that's equal to, 0.0, is equal to a quarter or a half or 1. What you find is that, yes, indeed, you actually see that this slope changes. So you might say the linearity changed, which could be a good constant, but you've also then decreased your transconductance. And again, this is not necessarily a bad thing, but it's something you need to be aware of. If you're trying to make something of high gain, then this is going to mean your transconductance will have decreased, and you can kind of see different values for transconductance depending on these different slopes. And again, I'm plotting this versus both differential voltage and the actual V1 minus 2, just so you can see that the one is half of the other. So you can definitely see these aspects, whereas if you were in subthreshold, what would it have looked like? It would have come down at a very sharp angle down here and worked its way down. So just what always happens is you always widen out the linear range. You also then decrease your transconductance. And it matters a lot on where you bias it on VREF. And this is directly a question of saying, how far above threshold am I? Right? Because the more I'm above threshold, the larger this value gets, and the wider my curve gets. So you can see quite a lot from this curve. And you can also see that this is not a trivial kind of problem to solve when you start doing some of the above threshold elements. And because of the squares, it's not trivial, but there are some nice identities and you can kind of work your way through it with some